Hi, today we are going to look at multiple representations of exponential functions. So it says graphical representation of the connections between table, rule of equation, context, and graph in chapter 2. You looked at the multiple representations such as table, graph, equation, or situation of linear functions. In this chapter, we're going to look at it for exponential functions. So let's look at some of the connections between multiple representations of an exponential function. Arnold dropped a ball during the bouncing ball activity and recorded its height in the table. Part of his table is shown at the right. What is the rebound ratio of his ball, and at what height did he drop the ball? Write an equation to represent his data. Explain your equation. So the first thing is we want to find the ratio, and so if you take 67.6 divided by 84.5, you're going to get 0.8. And so that's going to tell you what his ratio is. So then if you think about going backwards, it's what times 0.8 would give you that. So you would take 84.5, divide by 0.8, and then divide by 0.8. And so you'll see that he started at 132.03. Now, oh yeah, and here's an explanation of it too. So think about how to get this number right here, the 105.62, is think of 0.8 times what gives you 84.5. So then you could solve the equation, and that's where you get the 105.62. Then to write an equation, your formula for these will be y equals ab to the x. Your a is going to be your starting value, and your b is going to be your ratio or your multiplier. So when you look here, the starting value was 132.03, and then the multiplier, the ratio, was 0.8. So the formula would be y equals 132.03 times 0.8 to the x. Yes, so then a major technology company, XpoGrow, is growing incredibly fast. The latest prospectus, a report on the company, said that so far the number of employees Y could be found with the equation y equals 3 times 4 to the x, where x represents the number of years since the company was founded, how many people founded the company, and then what is the growth of the company, how can the growth be described. So the A, the number that's first, is, I call it the original number, the starting value. And so that would be 3. And then B, that's your multiplier or your ratio. And so you're multiplying by 4 each time. And that's how you get that. C, a computer virus is affecting the technology center in such a way that every day a certain portion of virus-free computers becomes infected. The number of virus-free computers is recorded in this table. How many computers are in the technology center? And then what portion of the virus-free computers is infected each day? And how many computers will remain virus-free at the end of the third day? Justify your answer. Okay, so the first question, how many computers are there in the technology center? Well, that's going to be the original number. So there's going to be 27 computers because none of them were infected on day 0. So there are 27 in the technology center. What portion of virus-free computers is infected each day? Well, you need to think about 27 times what gives you 18. So again, since you're multiplying the same thing each time, 27 times what takes you to there. So then when you solve that equation, 18 over 27, you can divide them both by 9, so you get 2/3. 2/3 remain uninfected. Therefore, 1/3 is infected each day because this number would be virus-free. And then the last question, how many computers will remain virus-free at the end of the third day? Justify your answer. So there's 12. So you would take 12 times 2/3, and you would get 8. So there will be 8 virus-free computers at the end of the third day. Tune in next for the next part.